Okay. So suppose we're going to think about exercise 2, okay? Now, the setting is this. You are in a country in Africa, which is called Angola, and you know that 12% of the population is left-handed. You randomly select a person in Angola, this country in Africa, and you want to determine if this person is right-handed or not. You are assuming in the setting of this research that no one can be both. Okay, so you are assuming that a person is, instinctively or primarily right-handed or left-handed, but they cannot be both. Okay. Now, the research means to identify the left-handed individuals as a success. Now, the first thing we are going to do is we are going to write each of us. So we are going to think now separately and individually, and then we're going to discuss. So each of us is going to define the Bernoulli that can describe this random experience. When we're thinking about defining a Bernoulli, we need to identify exactly when x takes value 1 and exactly when x takes value 0. So please go ahead and then we will discuss, okay? Okay, so if you are okay with it, I'm going to present you my suggestion. My idea is this, according to the common ground on our research. I'm thinking about a variable x, and this variable x will return to me the value 1 or the value 0. It returns the value 1 when one person selected randomly in Angola is left-handed. 0 when the same person randomly in Angola is right-handed. Do you agree?
Yes, Professor.
Okay. Now we need to identify, so we said that the Bernoulli is identified by these characteristics here. It is also identified by its parameter. So when we write x is a Bernoulli of parameter p, we say p is the probability of success. Therefore, the probability of x answering 1. Now, please go back to the exercise. Can you tell me the value of p in this case?
0.12.
0.12. Exactly. Yes. Everyone is okay with this?
Yes. Yes.
Okay. So the point here is there's nothing to work on regarding the Bernoulli, right? We already know when it answers 1, we already know when it answers 0, we already know what is the parameter that characterizes the Bernoulli itself. So there's nothing actually interesting to do. So why is the Bernoulli so very important for us? Because we have cases like this one. Now you will please read carefully exercise 6. So we're thinking about a team that, a research team from Lusófona, and they are studying the prevalence of diabetes in Algarve. They surveyed 10,000 randomly selected people in Algarve and concluded that 772 among those 10,000 people do in fact have diabetes. Okay. Now, we need to do the following. Firstly, we will write the Bernoulli that describes the experience, the random experience that occurs when we survey one of these 10,000 people that were randomly selected. Now, suppose we are working together. We need to agree with each other where we are going to signal the success. What is your choice? We are a research team. We have to decide. You decide. Where do you want to signal the success? If one of these people that we are surveying has diabetes, or if they do not have diabetes, what is your choice?
If they do have.
No, let's make it they don't. Sounds better, but
we can do it both. And what we are going to do is we're going to take one of the options here in class, and you'll do the math with the other option. So we will then compare, and we will do this throughout the semester until we reach the hypothesis tests and so on, to conclude that whatever choice we take, the conclusion will be the same. But at first, we need to agree on what we are going to do, okay? So let us suppose that we are going to think that the success is going to be identified when a person does not have diabetes, okay? So I would write X answers 1 if a person, a randomly, you already know what I'm going to write. So a randomly selected person in the Algarve, a randomly selected person in the Algarve among 10,000, has, does not have, right? Does not have diabetes. Does not have diabetes. Okay. Okay. And then we have 0 otherwise. Is this okay?
yes.
Let me just give you a small note here, and let me just point out something that is very simple. I'm sure you will agree. That is the other Bernoulli that we were talking about. Suppose that if a person randomly selected in the Algarve has diabetes, suppose we are describing this event as D. Okay, so I'm thinking like this. We have here the outcome space, which is the entire region of the Algarve. And we're thinking that there is a subgroup of people that have diabetes. And then there is the remainder of the people do not have, okay? And now what we're saying is in the variable X, we're saying X equals to 1 if this person belongs to the complement of D, so they do not have diabetes, right? And it's 0 if they do have diabetes. Now let us define the other Bernoulli. The other Bernoulli would be if a person that we selected randomly, etc., in the Algarve has diabetes, and so if they belong to D, right? And 0 otherwise. And what we observe is it's very simple, and it will also help us understand that whether we choose one way or the other, We will reach the same conclusions. And what I'm saying is, look at that. X tilde is simply 1 minus x. Do you agree? That's all it
Yes.
is. It's a kind of inverse. Can you see that?
Mhm.
Yes?
Yes.
Yes.
It's like we are making, we in mathematics, we call this a partition, you know? It's very important in science. We're thinking like, these people do have diabetes and these people do not. And what we're saying is that X bar identifies this, identifies this as a success, whereas X tilde identifies this one as a success. So they have to be one minus the other. Do you understand what I mean?
Yeah.
Yes?
Yes.
Okay.
Yes.
So now let me ask you something. Let us work with X, okay? If we work with X, would you agree if I write this? P is the parameter of the Bernoulli X. So it's the probability of a person in the Algarve having diabetes. Do you agree? My question for you is, please feel free to say that you do not agree, but I wanted you to think about this. When you think about this Bernoulli here, P, as we said, is the probability that X signals a success. So in this case, it is the probability of a person in the Algarve belongs to not to the complement of D, or probability of a person in the Algarve does not have diabetes. Do you agree?
Yes.
Does everybody agree? Or should I think about the probability of a person just among the 10,000 that we have? I'm asking you if P should be looking at 6, at exercise 6. Is P the probability of a person in the entire Algarve not having
Uh,
diabetes? Or is it the
No.
probability of a person among the 10,000 not having diabetes? What is the purpose of the research team? You are a data science. You have to work with this research team from Lusofona. What is their problem? Let me know. What is their question? Is it related to the probability amongst the 10,000? Or is it related to the probability in the entire region of the Algarve? What is it?
Among the 10,000.
I think the entire region.
Buhari, do you think that the problem that the research team is among the 10,000?
Yeah, that's the sample, but maybe they're going to make inference for the whole population. I'm not sure.
Yes, very good. So you're telling me that these 10,000 people that we have here are simply a sample of the entire population. The entire population is, we're thinking about everyone that lives in the Algarve, right?
Yes.
So the universe we're working with is in the random experiences. We're thinking about everyone in the Algarve, and we want to know the proportion, the percentage of people in the Algarve that do have diabetes, right?
Yes.
So the parameter P in our first variable, in our first Bernoulli is, okay, we need to know the probability of a person in the entire Algarve not having diabetes, right?
Yes.
Yes.
Now, it's true that we're only working with 10,000. So we have to find, let me stop here and ask if everyone is okay, if there are no doubts regarding the meaning of P. No doubts?
Okay.
Okay.
Just to clarify, so if the P is uppercase, then we're talking about the whole population.
Ah, very good question. No, that's not the point that we're making. No, Juan, let me just find space here, and you talk to me. Suppose let us read this second example to refresh reasoning, and then we'll go back, okay? Suppose you have a plant, and no, suppose I have a plant and I need you to help me, Juan. So my plant produces bottles for wine, for the wine industry. The wine industry is very important, as you know, in Portugal and worldwide. So the plant needs to produce high quality bottles and everything. So I'm worried about the number of damaged bottles I have in my production, because that affects my standing in the market and so on. I believe that my plant produces about 1% of damaged bottles, okay? I come to you so that you can help me understand if I'm thinking right or not. And then Juan, you tell me, okay, you will give me money so that I can check 2,500 bottles. I will go to your production. I will get to your plant. I will randomly select all of these 2,500 bottles. I will check each of them. And then I will be able to help you regarding this value that you have 1%. Now, tell me, Juan, what is the universe of your problem? What are the objects that you are worried about? Tell me.
I'm worried to know how many bottles are damaged, right?
So exactly. So your object of concern, let us say, are the bottles. The characteristic that you want to analyze in them is, are they damaged or not? So you have a very, very large production. You cannot go through the entire production of the factory. It's not possible. So you are going to select a sample, right? A subset. What is your subset? It's composed of how many individuals do you have in your subset?
2,500.
Exactly. And now you're going to look at those individuals, and you're going to apply to each individual, to each bottle, a Bernoulli. And your Bernoulli is 1, if the bottle is damaged, 0, if the bottle is not damaged. Yes? Tell me, when you think about that Bernoulli, let us write here. So we're thinking that we're working together, and we decided to do like this. 1, if the bottle that we are thinking about is damaged. 0, otherwise. Yeah?
Yes.
Now tell me, Juan, you have the universe here, that is the entire production of the factory, and you have a sample here, and here you have 205 individuals, and to each single one of them, you're going to apply a Bernoulli, right?
Yes.
Now, the point is, P is the parameter of each bottle being damaged. So this large P is for probability. This small p is a number, right? Between 1 and 0. It's a proportion. My question for you is, does this probability need to be assessed in the entire universe here, or just with regards to the sample.
I think on the sample.
But it does do we data scientists are we called to determine the value of P amongst 250 bottles, or are we using this heavy machinery of mathematics to determine in a larger universe?
Exactly,
In
larger
the
universe.
larger universe, yeah.
Juan, you are working to be able to, from the sample, extract information to apply to the entire universe, right? That's why you're working.
Exactly. Yeah.
So you're saying to the owner of the plant, listen, you have a problem here because if you produce like, imagine millions of bottles every day, which is possible, right? I have
Mhm.
no possibility of checking all of your bottles. What I'm going to do is you're going to give me enough money so that I can check these bottles and I'm going to look carefully at them. I'm going to determine the proportion amongst them that in fact has a damage. And then I'm going to get, heavy machinery from mathematics to be able to tell you if you're thinking right when you say that it is 1%. Do you agree?
Mhm. Yeah.
So the point here is this number P, that is the probability of a bottle being damaged among the entire production, is an unknown number. We have no idea what the value is, right?
Mhm.
And that's the difference between this exercise, and exercise 5. Do you agree, Juan? In exercise 6,
Yeah.
you want the probability of a person in the entire region of Algarve having diabetes. Do you know that
Mhm.
value? Do you know that number?
No,
No. You have a number amongst a sample, right?
the sample. Yeah.
Okay. So the most important thing for us, all of us, is to look, for instance, at exercise 5 and exercise 6 and see a huge difference. And the data science is all about this. In exercise 5, we can clearly determine P, and small p is relative to the probability of X giving us a success. In exercise 5, we can determine P, we can tell the value of P precisely. Exercise 6, we cannot. Let us see if everyone agrees, if everyone can determine the value of P for exercise 5. So we have this problem. Pedro has a method to decide if he's going on foot to university or not. So his method is the following. He starts the day by rolling 2 fair die, and if the sum of the numbers he gets from those 2 die is equal to 11, he goes on foot. Otherwise, he does not. Let us suppose I have a Bernoulli here, and that Bernoulli will signal when Pedro is going on foot as a success, okay? So I'm going to write like this. So my Bernoulli X equals to 1 if Pedro goes to uni on foot. 0 otherwise. Now, I have a parameter. I know that X is a Bernoulli, no doubt about it. There's a parameter P, and P is the probability of a success. So let us look at the characteristics of a success. Pedro goes to uni on foot, and that means that we need to have a sum equal to 11, right? So we're going to write here is a probability that sum of two numbers resulting of throwing two balanced die, etc., equals to 11. Is this okay if I leave it like this?
Mm-hmm.
Yes.
So I want the sum of two numbers that results from throwing two balanced die equals to 11. Now, I can get, I need to get
5 and 6.
5 from the first die. Thank you. 6 from the second, or
6
I
and
6 and
5.
5.
6, 5, exactly. Or, so now we're thinking about this as probability, classical probability, and we're thinking like this. The two die are independent from each other. So we're going to write like this. See if you agree. We have the probability of getting 5 or 6 plus the probability of getting 6, 5. Because there's no intersection between the two. We are saying that this is the number that comes from die 1, and this is die 2. They cannot occur at the same time. It's impossible, right? So the probability of the union is the sum. And now we're going to think like, okay, these two die, the results that we get from the first die do not impact the results that we get from the second die. Do you agree? There's no reason to believe that. So what we know from probability is that, okay, so what we need to do is determine the probability of the first die getting 5 times the probability of the second die getting a 6, plus the probability of the first getting a 6 times the probability of the second getting a 5. Is everyone okay? Or please let me know if there is any kind of question, please.
So can you explain why we're multiplying the probabilities again?
Yes, of course. Let me just get you some space here. Of course I can. So we're thinking like this, Ruth. In probability, we have, if you want to discuss this further, we can, okay? Ruth, let me know. So in probability, we have, we talked about, let me just open here a small note, and we're thinking like this. We have a random experience, and that random experience is identified with its outcome space omega, outcome space. Now, suppose, Ruth, you have an event, so a subset of omega, you have here your omega, and suppose you have a subset E that is an event such that its probability is positive. That means that the event is not, it is not impossible, okay? It is not impossible. And now you want to talk about a kind of probability where you are thinking about a certain type of conditioning. So I'm thinking like this, Ruth. I'm thinking about a timeline, okay? So time is occurring here. And I'm thinking like, okay, I know that E has already occurred. Imagine, I have taken a shot for measles when I was a child. Knowing that, what is the probability of me being infected, being sick with measles? Okay? So there is an event that occurred previously in the timeline. In this case would be, I have taken a shot for measles. I don't know if measles is read. well written, but I'll check it out. And now, knowing this back in time, I want to determine what is the probability of me becoming sick. So it is another event, okay? This is called the conditional probability, and we write it like this. I want to know the probability of F occurring, knowing this is a vertical bar, and it states that we know already. So this event that I'm writing on the right has occurred, okay? It has happened. And because it has happened, I want to determine what is the probability of the other one, okay, Ruth? And
Yes,
we,
Professor.
yes, and we write it in math like this. It's, well, I want to know the impact of F on E, and we're going to divide it by the importance of E. Now tell me, Ruth, this is very, very simple. Let me ask you something. Suppose this is very, very simple. Just two more ideas, and I think it will be clear. Now, the first idea we need is when you look here, you can clearly see that if I multiply this to this side, I get the probability of the intersection. Can you see that?
Yeah.
So the probability of the intersection will be the conditional probability times the probability of E, right?
Yeah.
Now tell me, Ruth, if I ask you a question, this is intuitive. Suppose you are thinking about a timeline. I have an event E and I have an event F, and I tell you, listen, Ruth, I believe that E, F are independent. So I therefore believe that if E has occurred, it won't impact F. If F has occurred, it won't impact E. That's my reasoning towards independence. Now, what would you write about this then? I'm telling you that E has occurred, and now I want the probability of F. But I've just told you that they are independent. So what do you think? I tell you, okay, Ruth, I know that this has occurred already. And then I tell you, oh, but I believe these two are independent. And then I'm asking you the probability of F. If this doesn't impact this, what do you believe is the relation with this?
That would be the probability of F bar E with the bar on top of it.
If I'm asking you like this, Ruth, I tell you something like this. Listen, Ruth, I believe that the time you arrive at the probability, I believe that you arriving on time at uni is independent of the fact that I also arrive on time at uni. I believe that they are independent. And then I'm going to write this. I'm going to ask you this. Good. I want to know the probability that you arrive on time, knowing that I arrived on time. I think you would tell me, this is absurd. You think you're crazy, Sophia? If we are independent, why do you care? What does the fact that I arrive on time depend on you arriving on time, right?
Yeah.
You would say, this is completely unreasonable. This has no impact over this, right?
Yes.
And so you would say here, listen, if they are independent, this event E has no impact on F. So this probability, this conditioned probability is equal to this. Do you agree, Ruth?
Yeah.
Like here, you would tell me, listen, the probability that I arrive on time is completely independent of whatever you are doing in Lisboa. It has no business in my life, right?
Yes.
So in mathematics, we would just write, coming from here, we would write like this. Okay, if you have two events that are independent, the probability, the conditioned probability is simply the probability itself because they are independent. And now you use this here in this expression, and if they are independent, you would get the probability of F times the probability of E is the probability of the intersection. Can you see, Ruth?
Yeah. Yeah.
So if you want to get a 5 from die 1, and so we're thinking here, Ruth, we're thinking here, like, I want to get 5 from the first die and 6 from the second. They are entirely independent. So it's the probability of getting a 5 times the probability of getting a 6. And the same thing occurs with the second pair, right? Because the second pair is 6, 5. So it's the same thing. See?
Yeah. Thank
You
you,
see?
Professor. Mm-hmm.
Yeah. So here, from here to here, we use the fact that they cannot occur at the same time. And from there to here, we used independence, right? You agree?
I agree.
And now here I have 1/6 times 1/6 plus 1/6 times 1/6. So 2 times over 36, 1/18, right?
Yeah.
And the matter is, we can determine P with no problem. There's no doubt regarding P. These problems are not the ones we are paid for. Data scientists are paid to research on problems where P is not known. Something like this, 6. Something like this, 7. And something like exercise 8, which I also left there for you to think. Okay? Is that okay?
Yeah.
Okay.
Yeah.
Okay. So if you agree with what I'm going to suggest, I think we should stop now